So, continuing our discussion, we had discussed how to draw the efficient frontier considering 4 combinations: short selling allowed, not allowed for actual risky assets, and short selling which is in technically lending borrowing being allowed for the risk free interest rate, which is RF. Now, what if we have different other combinations? So, if we consider the slide which is shown, you have basically either optimizing or trying to basically find out the best return or best risk. Risk means you are trying to minimize, return means you are trying to maximize. Considering that if the dividends are greater than equal to some D star value. So, what we actually mean is either you want to basically minimize the risk, that is the variance, or maximize the return, which is expected value. Now, till now we have considered the subject to consideration is that summation of the portfolio returns being greater than equal to some R P star, star means value which changes. Similarly, for the double summation, which is the variance of the portfolio being less than equal to some sigma square star P, P is the suffix, and so on and so forth, where the weights are equal to 1, then weights are either between 0 and 1 if there is no short selling, if there is short selling obviously that changes. So, another case can be where it is greater than some fixed D star value of dividend which we want for our case, or it can be, say for example, there are costs involved with respect to buying and selling stocks. So, obviously those things can be considered, and rather than solving the nitty-gritties of that, we will once the overall the course content for the options are over, we will include few of the interesting problems with their actual formulation and also with their solution techniques for some of the data sets considering from the stock markets throughout the world. Like we can consider NSE, which is the National Stock Exchange, we can consider the BSE, we can consider DAX, we can consider the CAC, we can consider the Dow Jones, so on and so forth. Now, another alternative solution method has been proposed by Lintner. Now, if you remember why we are going to consider that, let me step back a few lectures or one and a half lectures before. We considered that the concept of short selling was there, and we also considered that in order to find out the actual weights, we normalize them and found out the normalized weights such that the sum is 1. Now, as SS, which is short selling, involves putting an amount of money on equal proportions for the short selling, the Lintner methods proposes that if you borrow an asset or a financial asset from a person, obviously there has to be some risk for the other person. So, in order to compensate that, there should be some collateral. So, considering that collateral concept is there, and if you want to incorporate that in as a short selling concept as well as an optimization concept, Lintner has proposed a model where the sum of the mod of the weight should be equal to 1. So, rather than only the weights, we should basically consider the mod of the weights is equal to 1, and obviously there are solution techniques for that, but we will consider a very simple solution technique based on which you can solve this problem. The two important points about which we should be concerned while implementing the portfolio theory or trying to basically analyze the best optimum portfolio or trying to find out the efficient frontier, either or trying to find out the best set of solutions or trying to find out the minimum variance point or the maximum the maximum risk return concept, which is Q. We should basically consider the simplification of the amount and the type of input data needed to perform portfolio analysis, and simplification of the computational procedure needed to calculate that. Now, remember, till now, even though stock market prices are non-deterministic, that means they are changing, we have considered very simply that a priori the values are given, and based on that we are doing our calculations. Later on, we will just relax this consideration. Like I said, we will consider dividend policies to be true, we will consider non-deterministic concepts of stock prices, hence the returns, we will consider some distribution of the returns, whether and as well as the parameters of the distributions or return are changing. We will consider buying and selling of stock are there as a part and parcel of our investment policies. So, once we understand the general formulation, we will see that they can be done for variety of problems. Now, to solve the above mentioned problem sets, all what we discussed, initially we will consider the single index model and the multi index model and few of the averaging techniques. Now, in the single index model, which as the word says, there is some single index or some single variable based on which you can find the prices of the stocks or the returns, and based on that you can proceed. So, another assumption, the most important assumption is that the co-movement between the stocks is due to only a single common stock, which is the index we will consider. These models are not only used to estimate the correlation matrix, but also used to find out the efficient market test and try to find out the best optimum solutions of the portfolio, such that we are almost equal to the market as we basically formulate our portfolio, considering different types of stocks are there. So, if you remember in class 10 and 12 we have considered the equation of a straight line as equal to y is equal to mx plus c. Now, if we had drawn that curve, it was like this, where this value, the height where the line cuts the y axis is known as c, and if you consider the tan of this angle, which is the slope, this value is given by m. So, what we are trying to find out is, given different values of x which are along the straight line, we want to find out what are the values of y. Now, in general we would consider that over and above the movement of the stock prices, or over and above movement of some random variables, there is some white noise also. So, in the concept of simple linear regression, multiple linear regression or simple linear regression, we consider there is a x which is a random variable which is independent and known to us, we have the data sets, and there is another random variable y which is a dependent variable, such that there is some relationship between x and y, such that given x we are able to find y. Now, our main task is basically to predict or estimate or forecast the value of y to the best possible extent, which means that if we have set of x's for different time periods, we also have the set of y's for those same time period. Now, consider, given that information, we want to find out some relationship functions between x and y, such that in the future if we have x, that means given n number of x, we have already n number of y's. Now, in the second stage, use the information of those n number of x, try to find out the information for relationship between x and y. And then when we get the nth plus 1, nth plus 2, nth plus 3 x, we are able to predict, forecast or find out the predicted value or the estimated value of y to such an extent that some rules are met. Now, if I ask you very simply that what rules would you like to basically meet for your prediction, obviously very intuitively everybody will say that our predicted value or the estimated value should be as close as possible to the future actual value of y, which means the difference between the predicted value and the future value, actual values y, should be as low as possible, which means that we want to basically minimize the error. Now, the word error is being used here, which is a proxy of the overall variance we want to basically minimize. So, our main task is basically to find a model, so that we are able to find out the set of relationship function between x and y, such that the overall area error is minimized to the maximum possible extent. So, let us consider a very simple equation between relationship between x, which is the return for any particular stock, and which is y, which is basically the market. Because if you remember in the last slide, we discussed that there is some variable which is independent, which is the market, which gives us the best amount of prediction which is happening between the return of a particular stock and the market. Now, here RIs or small RIs are the return of a particular stock with a suffix I, meaning the stock number. And RM is basically the conglomeration of all the market which you have, which is known as index, which as we said that it can be the Bombay index, the National Stock Exchange, can be, say for example, Dow Jones Industrial Average, can be Nikkei from Japan, can be FTSE from UK, so on and so forth. Now, there are a few assumptions, and if you go to the fundamental principle of linear regression, we consider that intrinsically x has a distribution which is normal. X means the RM which we have. So, RM has a normal distribution, which if you remember we mentioned that if the utility functions are quadratic, then only you can say the returns are normal. So, we will consider RM as normal distributed with some mean and some standard deviation. We will have the returns of the stock RIs as also normal distributed. So, if you remember, if you can recollect from very basic concepts we have done in engineering or in MCom, BCom, we will consider the normality or normal distribution as a property such that any convex combination of normal distribution will always result in a normal distribution. So, what we are trying to do is that we are trying to find out some relationship between Ri, which has normal distribution with certain mean and certain standard deviation. Along with that, you want to find out what is the independent variable, which is Rm, which is the market, which is also normally distributed. Now, if you find out this, the equation along with the graph which you had drawn for y is equal to mx plus c, then alpha is akin to c, beta is akin to the slope, and this epsilon which you see here in this single index model, which is not there appearing in the case for the simple equation y is equal to mx plus c, it basically means white noise. That means there is some fluctuation, and this white noise under over which we have no control, and this white noise basically gives you the overall randomness in the overall process, over and above the randomness in the values of x, which is Ri, or values of y, which is Rm, and value of x, value of x would be basically Rm, and value of y would basically be Ri. Now, the assumptions are very simple. You consider in the long run the expected value of the white noise is 0. That means epsilon, which is the white noise, if you add up the values, they add up in the long run as 0. We will also consider that there is no covariance existing between the market and the white noise, because that is the second equation. We will also consider that there is no correlation coefficient existing between the ith white noise and the jth white noise. Now, and finally, we will consider another two which we will consider is that the variance of the white noise which is given is time independent, which may not be true in actual relationship, and we will consider the market has a variance which is known as the market variance or market risks as such for the market only, which is given by the variance sigma square suffix m. Now, if you look at the third one, and if you have basically n sets of equations, in the sense I have y1 is equal to alpha 1 plus beta 1 into Rm plus epsilon 1. Then next case we will basically have y2 is equal to alpha 1 plus beta 1 Rm plus epsilon 2. Now, remember this 1, 2, 3, 4 for y is basically the data point, which is changing from 1, 2, 3, 4, 5, 6, 7, 8 till 9, while epsilon is also in the same case, but the differentiation which we want to highlight is basically alpha 1 would basically be the so called c value for y is equal to mx plus c for the first stock, while beta 1 would be basically the market risk or the beta value for the first stock. So, if you have 10 different stocks, the equations would be, there would be n such equations for the first stock, n such equations for the second stock, and so on and so forth. So, we will consider the first stock only, and that should basically give us all the information and all the concept how we are able to solve the problem. Now, given this, our main task, if we basically denote it in a matrix notation and format, what we have is basically y, which now is a matrix, is equal to alpha, again it's a constant value, remember that, is again a vector, y as such is a vector, and you have basically a vector of beta into x plus some vector which is basically epsilon. So, what we have, y is a vector of cross n cross 1 depending on the number of readings which you have, and beta is also, when beta into x also multiplied, is basically n cross 1 matrix depending on the data size. So, obviously, you can find out what are these values which you have for beta, what is the rank of that, what is the size of that, so on and so forth. Similarly, we will have epsilon. Now, if you write in the concept of vector notation and you want to solve them, then generally we know there is a method of Gauss-Jordan multiplication, where the concept of determinant or the value of the determinant is very important. Now, in the value of finding on the value of the determinant, we want to basically find out the inverse and so on and so forth. Now, finding on the inverse, important concept comes is that rank of a matrix. So, rank of a matrix is very simple concept, where the number of rows and number of columns are such that all of them are independent. So, if they are not independent, as finally when you are trying to solve the equation in the simple linear equation format, technically you should have basically n number of variables. This n and what we have written are different. So, this the first n which we discussed was basically the number of data points, and the second n which we are talking, or let us consider as k, is number of variables which you have. So, for that matrix, when you solve, if there are k number of such equations and k number of variables, they should be independent in the sense that all the k variables which you find out would be unique. In case they are not, obviously it would mean the rank is not k, such that there may be some equations where the independent characteristic may not hold true, and that we will see would basically give us some information whether the concept of multicollinearity, collinearity, homoscedasticity, heteroscedasticity would hold or not. So, we will later use these terms in the time series concept. So, this relationship between the error should be such they are not dependent from one to other. So, if they are dependent, obviously the whole structure of the problem would basically collapse. So, we will consider this case where both the covariances between the so called market along with the white noise, as well as the covariances between the white noise from time to time would definitely be independent, such that the values are 0. Now, if you find, okay, let me go back again. If we use find out the expected value, so what we will have, you will use the expected value of this is equal to the expected value alpha, which is a constant, alpha is a constant, plus beta again we will consider as a constant, which is the tan of the slope, tan of the theta, which is the slope. Then Rm is a random variable, obviously it will have a expected value, and the last term, which is the white noise, would basically be 0 according to the first assumption. So, if you find out the first expected value, you have this equation where R bar or expected value of R, whether it is stock 1, stock 2, stock 3, that is the question, is equal to alpha with a suffix depending on the stock number, plus beta suffix stock number into R bar m. Now, if you want to find out the risk, so if we go to the first equation again back, so they would be on the left hand side would be the risk of the variance of the stock, and on the right hand side technically we have 3 so called random variables, even though we will see that one of them are technically deterministic, but let us consider whether they are random or not. Alpha is not random, so it is a deterministic one. Rm is a random one, so we need to find out the variance of the covariance. Epsilon is also random, so we need to find its variance or covariance. Now, if they are 3 such variables, one of them being deterministic, another being 2 being random, so basically you have a 3 by 3 matrix. So, the first element, which is the variance of alpha, would be 0 along the principal diagonal. The second element would basically be the corresponding variance of beta I into Rm, and the third one would be the variance of white noise. While the off the diagonal element all would be 0, because we have considered 2 things. Covariance of the white noises are 0, and covariance of these also are 0, as well as the covariances between the Ri and the epsilon. So, once we consider that, the second equation would basically give us the variance of the particular stock, which is consists of 2 terms. One is beta 1 square into sigma square m suffix m plus sigma square of epsilon. So, now we basically should make a note of these 2, about which we will discuss in few moments. While the covariances existing between the two stocks, say for example, in BSE you are taking Tata Motors and you are taking Reliance. So, obviously the covariance existing between them would be given by the values of basically betas multiplied for both of them into the market risk. So, what we are trying to do is that if you see that we are trying to replace overall risk of any 2 different stocks or any particular stock by a simple concept of market variance only on the market risk. And if it is only a single stock, we see that it will basically consist of 2 terms. One is the risk coming from the market, and one is the white noise, which you cannot control. And when you want to find out the covariance or the risk of one particular stock with the other, which is the covariance, you will find is basically being multiplied by the variance on the market and the 2 different values of beta which you have. So, consider this very simple example. The months are given on the first column, sorry, and the returns are given on the second, and returns of the market are given in the third, and you basically utilize the equation which is equal to Ri is equal to alpha I plus beta I into Rm plus epsilon. So, you consider alpha as 3 constant, beta as 2, you find out these values. And the reason I am trying to highlight with this simple equation is that even though it is a theoretical one, the important point to remember is that sum of the error should definitely be 0. Now, having said that, what I want to find out later on also is that what are the different type of methods we use. So, first let us very briefly go through the concept based on which we are trying to solve. Now, in linear equation what we have, if you want to make go into the depth of this, is basically given any equation y is equal to alpha plus say for example beta x plus epsilon. So, we have basically n number of equations. So, basically it is yi, then it is xi and xj, let me rotate xj, this is basically j, this is j, this is comma I, and j is basically for the number of stocks which is 1 to k. Now, what you actually do is that given this n number of data points, you find out the values of beta and then basically replace beta which beta hat which is the estimated value, and for the nth stock which you want to find out nth plus 1, you use these beta values, beta hat values along with the value of x for the jth stock for the nth plus 1 time in order to basically predict y which is basically for the nth plus 1 time. So, what we actually do is find out the difference of the errors between the real value and its predicted value which is y hat, and you basically take the square of that and minimize that. So, once you minimize that, your actual equation would be differentiating with respect to all the beta values which you have. So, if you expand this equation, the first y would be the actual value and the y hat value within itself would basically have the two unknowns which are basically alpha and beta. So, what you do is that differentiate with respect to alpha or beta whatever it is and equate to 0, and then find out the second differential and basically try to find out the minimization one. Now, if you remember that why we are taking the square, if you remember the concept of a simple variance, what we are trying to do, we are trying to basically minimize the variance to the maximum possible extent. So, this is basically known as the concept of ordinary least square method, and here in the ordinary least square method we basically try to find out the errors in such a way which the errors are the square of the differences of y and y hat, sum them up. So, this what I am using is that this is basically a vector. So, if I basically have the scalar points for each and every data set, it will basically be summing up all the errors which you have for all the number of data points we are going to take, and then sum them up and differentiate with respect to all the variables which are unknown to us and equate to 0 and find out those alphas, betas and so on and so forth. So, once those alpha and betas are found out, you find it for the nth plus 1 and then proceed in such a way that you are able to plot the point, keeping in mind your main focus was trying to basically minimize the variances. Now, consider, so given this what we have is basically there is the ith stock. So, such ith stocks are there in the market, and using these ith stocks in different proportions for say for example 10 of them, we want to basically formulate the portfolio. So, if you consider the BSC 30 or say for example NSC or CACs or DAX whatever it is, there are different type of stocks which are there inside those conglomeration of the market index which you have. And when you combine them, what you want to do is that find out the overall portfolio which you are trying to formulate with respect to the risk of each and every individual index which is there in that portfolio with respect to the market, and also find out the risk of the total portfolio which is being formulated with respect to the variance as well as the beta values which you have for each every stock. So, if you have the equation for the first the index using the single index model, what you actually have is this R1 is equal to alpha 1 is equal to beta 1 is equal to Rm. So, these are all bars and these alpha 1 and beta 1 are constant. Similarly, you will have basically R2 is equal to alpha 2 is equal to beta 2 into Rm again bar. Now, if you consider all the particular different type of stocks which you have in the portfolio, if you remember the portfolio consists of say for example k number of stocks and each is being invested in proportions of W1 to Wk. So, when you multiply the corresponding alpha values, multiply the corresponding values of betas Rm, they would be multiplied by the corresponding weights which you have. So, when we have the return on the portfolio with respect to the single index model, you will find the overall alpha for the portfolio which I am highlighting now will be equal to the weights for each of the stock in that portfolio multiplied by the corresponding alpha i's which you have for that particular stock. While the overall the returns which is coming from the market, which is going to affect your portfolio, would be equal to Wi beta I into Rm bar, where I changes for all the stocks. And if you consider this and expand that, what you will have is basically the beta p. So, what we are trying to replace, the alpha i's and the weights had been replaced by alpha p, which is the portfolio alpha, and the betas and the Wi's and the Rm's which you have formulated, basically that gets replaced by beta p multiplied by the so called the return of the market. So, what you have actually done is replaced any portfolio you can formulate by alpha p of that, which is in relationship with the market, as well as equating it to basically beta p, which is the portfolio's beta with respect to the market. Similarly, if you find out the variance of the portfolio, it will basically be considering of these two terms. I am going to highlight these two terms. They are almost similar, because in the first term, if you see, you are taking I as 1, as 2, and so on and so forth, which is the principal diagonal, and the second terms you are considering is basically in a very simple way is equal to the covariance concept, which is of the diagonal alignment. And the third one is basically which is with respect to the white noise. So, what we have is basically a whole amount of risk which is coming from the market. I am not using the word market risk, I will come to that later, and one would basically the white noise risk, which we want to basically over which we have no control, but we will try to see that how we can basically make a control over that. So, thus if the portfolio P is taken to be market portfolio, that is all the stocks held in some proportions as in relationship to the market, then the expected value of the portfolio, if it is exactly equal to the market, would be Rm. Hence, if you are able to formulate a portfolio such that its beta is exactly equal to the market, which means that it mimics the market to the maximum possible extent. But in generally that would not be true, and we will try to formulate portfolios such that they are theoretical as close as possible to the market, but in practical sense they may be some difference. We will try to basically analyze that in detail.